So this is a talk about a joint project with at least Sarah Brauner, Patricia, Commins, and Franco Saliola. Several other people have contributed previously to papers we're building on, so you will see a lot more names here. The slides are on my website, the ones you see, and the paper is on the archive. I think it's in a pretty finished form, but there might still be simplifications appearing in some time. So this is a short version due to the 25 minutes. I will be mostly talking about the symmetric group algebras, not about the q-deformations. So here is the setup. You have a commutative ring K, can just as well be the rational numbers. This is not super dependent on K. Then for every finite group G, there is something called the group algebra of G over K, and I just call it K brackets G. So, for example, if G is a symmetric group S3, it consists of formal linear combinations of permutations, and they're multiplied using the product in the group, so composition of permutations. And they're added just as formal combinations. So you're basically taking the linearization of the group. You're taking formal linear combinations of group elements. If you have not done group algebras for a while, keep in mind that this algebra is not isn't particularly simple. It has zero divisors. It has various weird factorizations. Things are often equals that you wouldn't expect to be equal. So it's an interesting thing to study, and people have studied this group algebras a lot. It's basically representation theory is half about group algebras. So for us, it's important that every element of the group algebra, let's say A, gives rise to two linear maps from the group algebra to itself, called L of A and R of A. L of A left multiplies the input by A, and R of A right multiplies it by A. So they're linear maps. And if you using the basis of the group algebra, you can just encode them as matrices of size G cross G, basically. Big matrices, but matrices nevertheless. So they have all the nice structures that matrices have from linear algebra. They have kernels, characteristic polynomials, eigenvalues, eigenvectors, and so on. And in fact, it doesn't matter that much whether you're doing left multiplication or right multiplication. LA and RA have the same eigenvalues with the same multiplicities, so you can just call them the eigenvalues of A. One more general feature that group algebras have is the antipode. That's just a linear map that sends every element of the group to its inverse. And it's usually when you apply this map to an element, you call it A star. So the star is the map. Notice that A star star is always A, so this is an involution. And also A B star is B star A star, so it is an anti-automorphism of the group algebra. I will be talking about symmetric groups in this talk, not arbitrary groups. So here are some notations. This is standard algebraic combinatorics notation. And the symmetric group Sn is the group of all permutations of the set bracket n multiplied by composing them. A lot is known about the symmetric group algebra. It's definitely something you probably have seen a lot. How do I clear all drawings? Okay. So I'm giving a bunch of references. Everything red you can click on if you download the notes. But we will be focusing on specific elements here in this talk. One classical family of elements, maybe the simplest interesting family, are the so-called Young-Gutzes-Murphy elements, YGM for short. They are obtained by summing a bunch of transpositions. JK is the sum of transposition 1k plus transposition 2k plus and so on, plus transposition k minus 1k for each k from 1 to n. In particular, J1 is an empty sum, so it's 0. Also notice that they're all preserved by the antipode because the transposition is self-inverse. It's an involution. Now, here is the first easy but not obvious, maybe unexpected fact. The transpositions themselves don't commute, but their sums, the JKs, commute. Then something even weirder, and this one is actually not trivial at all, that the eigenvalues of JK, at least over the rationals, are these integers. So this you can think of a JK as an n factorial by n factorial matrix, because this is n factorial is the size of the group. Normally, it would have n factorial eigenvalues, and they would be weird algebraic integers. Yet, in this case, it turns out it has pretty few eigenvalues, so they have pretty large multiplicities, and they are all integers. This is surprising, I would say. And even eigenvectors can be described explicitly. This is the famous semi-normal basis of the symmetric group algebra. It has to do with the reducible representations, the standard Young tableaus, and so on. Now, before I move on, I want to mention that elements of the symmetric group algebra have a meaning. Well, many meanings, but one of them is probabilistic. You can think of them as shuffled or as random shuffles of decks of cards. In fact, a permutation can be viewed as a deck of cards, and an element of the group algebra is a linear combination of permutations. So you can view it as a random state, where every state sigma appears with probability a sigma. Of course, you have to normalize the a sigmas down to 1. You have to make sure that they're non-negative, but yeah, unless you like negative probabilities. Now, if you take this further, endomorphisms of the vector space case and become random shuffles, so transformations, Markov chains, basically, sending random decks to random decks, L of A becomes a random shuffle that basically looks at the labels of the cards and acts accordingly. R of A looks at the positions of the cards. For example, R of JK is swapping the case card from the top with one of the cards above it, and which one is chosen uniformly at random. Here is another family of interesting elements of the group algebra of the symmetric group. There's a so-called k-bottom to random shuffles. So here is one way to define them. It's the sum of all permutations sigma in the symmetric group, such that those inequalities are satisfied. What these inequalities say is that if you write sigma in one-line notation, then the numbers 1, 2, ... n minus k appear from left to right. All the other numbers can appear anywhere in any order. In particular, if k is n or n minus 1, these inequalities are tautologically satisfied. There are no inequality signs here. And so you're just summing over all the permutations. If n is 0, the inequalities force sigma to be strictly increasing, so the only permutation you're summing is id, the unity of the algebra. And if k is 1, you're kind of close to it, but you're not at it. You're summing a bunch of cycles that all have the form n minus 1 ... to some I and back to n. This has an extra name. This is called Bn. So as a random shuffle, Bnk takes, or rather right multiplication by Bnk, takes the bottom k cards and moves them to random positions. And its antipode, Bnk star, takes k random cards and moves them to the bottom k positions. This is a general rule. The antipode of a shuffle is just doing the shuffle in reverse. So Bn equals Bn1 is known as the Zetlin library. I think bookshelf is probably a better way to call it, because you can think of it as a shelf of books where you pick a random book and move it to the front of the shelf or to the back of the shelf, whatever you call it. And people have actually used this. This appears every once in a while. It appears in Lie algebra cohomology. This kind of operation is similar to how, like in the Kossel complex, the delta takes an arbitrary factor and puts it on the left. It has appeared in a model for computer memory, and like when you access a piece of memory, it's forwarded to the beginning of the heap, so to speak. So it's a pretty natural object. Those B and Ks have been studied excessively. In particular, the highlight, I guess, is that the eigenvalues of Bn are those n numbers. Yes, you're reading it right. This look like n plus 1 numbers from 0 to n, but n minus 1 is actually missing. And all the other Bnks are just polynomials in Bn. So knowing the spectral theory of Bn gives you everything about the Bnks as well. In particular, they all commute because they're polynomials in a single thing. So there are many proofs of this by now. I've written one on mass overflows. There are many in the literature. And you can, in fact, compute even the multiplicities of the eigenvalues. The eigenvalue k appears as often as there are permutations with k fixed points, which is, by the way, why n-1 doesn't appear, because the permutation with n-1 fixed points would actually have n fixed points. So think of it as multiplicity 0. So as you see by now, the antipodes are doing the same shuffling, but in reverse. So now you're doing, you're picking k random elements and putting them at the bottom. But taking the antipode as an algebra anti-automorphism, so any algebraic properties are more or less preserved. And also, if you don't like the bottom of the deck, you can take the top of the deck instead. It boils down to a conjugation. Again, you don't get any new theory here, you just get a conjugate version of the existing results. So yeah, this is probably these are the two first papers, I think, about those shuffles. By now there are many. Now, our work, even so we have recovered some of the results about the bees, we are actually concerned with the random-to-random shuffles. Right away, I can tell you what they do. They pick k cards from the deck and move them to k randomly chosen positions. And both the cards you pick and the positions are random uniformly. So the way to define it combinatorially is this. You're summing all permutations sigma multiplied with the number of so-called non-inversions of size n minus k. What is a non-inversion? It is basically a strictly increasing subsequence of length n minus k. So it is a subset of size n minus k on which the permutation is increasing. Here is R42 as an example. In this case, you're looking at 4 minus 2 element subsets that are increasing. So basically, subsequences of size 2 that are increasing. For example, 1, 2, 3, 4 has 6 such. 2, 3, 4, 1 has 3 such. You can have 2, 4. You can have 3, 4. Oh, and 2, 3 as well. One permutation doesn't appear at all, which is 4, 3 to 1, because there is not a single increasing subsequence of length 2. So you don't see it in the sum. Every other permutation appears with some coefficient. Yeah, again, you get it if you take k equals 0. You get the sum of all permutations if you take k equals n, and you get the sum of all permutations times n if you take k equals n minus 1. None of this is interesting. The interesting RNKs are in between those extremes. So here is the first mystery, and this one has been a real mystery for a long time. Reiner, Saliola, and Welker first discovered it, and they proved it in a way not many people understand, that this RNKs all commute for a given n. This time, this cannot be explained by them being polynomials in Rn1. They're not polynomials in a single one of them. The next mystery is that their eigenvalues are again integers. For example, if you look at the eigenvalues of Rn1, they are integers between 0 and n square. Not all of those numbers are taken, but all of the eigenvalues are in the set. So this was published in 2011, Memoirs of the AMS. I think the second claim was a conjecture back then, but Dieker, Saliola, and Lafrenière, Lafrenière and her PhD thesis finished that proof. What I will be talking about are those two recent preprints where these things are first reproved and secondly generalized to Q, meaning from the symmetric group algebra to the Hecke algebra. In particular, our proofs are also more elementary and easier. I say more elementary, they still need some representation theory for the eigenvalues, but more elementary in that the commutativity, for example, you can just read it. It's not, you won't have to do a lot of digging. The first step, and this is known long ago, is you recognize that R and K is actually B and K times its antipode divided by K factorial. And probabilistically, this is obvious. If you want to pick k random elements and move them to k random positions, you can first move them to the k bottom positions and then move them back to random positions. However, this does not give you commutativity because those do not commute with those. Now, maybe this doesn't look very nice, but this is in a way the key to our proof. Bn Rnk equals this kind of annoying formula times Bn. You can think of it as a way to commute an Rnk past the Bn, but the other thing you will notice here is that this is mostly playing out in the symmetric group algebra of 1 levels lower, Rn-1k and Rn-1k-1. So this lets you do an induction on n. And this is a young Eustace-Murphy element, which is, of course, this is not in the smaller symmetric group algebra, but it happens to commute with it, so it's kind of nice. It's almost like a scalar. This was noticed in the first long paper, which actually grew out of an RU project at UMN. It's inspired by the previous work, of course, but they moved this work to the symmetric group algebra, whereas previously it was some weird operators acting on representations one at a time. And the proof is not very hard because ultimately you can kind of compute those things. You have to match addends by addends. It's not very fun. Ultimately, our proof requires a lot of lemmas. None of the lemmas is very difficult. Yes, a lot of sum computations, basically. Now, this recursion does not compute Rnk, but it gets us close to it. The other thing that you easily notice is that Rnk is Bn star times something if k is non-zero. K is 0 is just it, so you don't care about the case, but it turns out that you can use this recursion to prove that the R's commute. The argument is kind of neat. I don't have much time for it, so I'll just let you just sketch it. If you want to prove that the Rni Rnj is Rnj Rni, well, you can put on Bn on its left as a catalyst, and then you use this recursion to commute the Bn to move it past them. But when you move it, the R's don't stay R's. They become those unwieldy terms, which I call W's. But these unwieldy terms are sort of coming from one end smaller, and so you can use induction to show that they commute. That's the induction hypothesis, basically. And so you get that kind of commutativity from the induction hypothesis, and so you get the R commutativity, well, up to a factor of Bn on the left. And you can get rid of that factor with another nice trick, with the fact that you have a hidden Bn star factor here, and then, you know, this is maybe familiar to the linear algebraists in the room. You can actually get rid of this Bn factor. Well, we have a less tricky proof as well. It's ultimately with this formula, it's not a very difficult problem anymore. So much for commutativity. Now, why are the eigenvalues integers? Well, we have two proofs. One of them is quite elementary, and I think it's interesting in that it actually gives a new method for proving that eigenvalues are nice. However, it does not give you the actual eigenvalues with their actual multiplicities. It gives you many phantom eigenvalues, so things that could possibly be eigenvalues but actually aren't. Whereas the other proof, much more technical, actually gives you all the eigenvalues using the semi-normal basis. This is what my co-authors did, that's other proof. I have nothing to do with it, and I'm still in awe about how anyone could find it. This is the result of the second proof, and I'm not going into details. I just want to give a little mention of what things appear in it. So first of all, the eigenvalues of R and K are indexed by the horizontal strips of shape lambda over mu, where lambda is a partition of n, and mu is a smaller partition that has at least one disarrangement tableau. Then you're looking at the contents of certain cells of the skewed diagram, and then you're taking products and sums of these products. And you can also compute the multiplicities of those eigenvalues in terms of numbers of tableaus. Yeah, I should say that the size of lambda should be n, of course. I forgot it for some reason. Okay, so horrible formula, right? Well, it gets worse because we can q-deform the whole thing. And the q-deforming many things is easy. Numbers just become q integers. But q-deforming the symmetric group algebra is not that easy. And the answer isn't that old. It's called the Hecke algebra or Rivahori-Hecke algebra. I'm not going to, this is not going to make any sense to anyone who has not seen Hecke algebras, so I will skip a lot of the definitions. I will just say that it is still a free K module of rank n factorial, so it kind of has the same basis made of permutations as the symmetric group algebra, but the multiplication is now more complicated because there are error terms. You are not just composing the permutations anymore. And still, you can still it has a nice structure theory, at least when Q is not a root of unity and not zero. It still has an antipode that takes permutations to their inverses. It still has Young-Gutz's Murphy elements. Their eigenvalues are still nice, but instead of the integers, you get the Q integers. It still has bottom to random shuffles, and their definition is literally the same as for the symmetric group algebra. Normally, when you q-deform something, you would expect a power of q to appear somewhere, but nope, no weights, same sum. They still have the nice properties, but again, the eigenvalues are not the integers 0 to n, but the q integers. Yeah, you get interpretations that are Hecke specific. So when Q is a power of a prime, there is an action of this on the flag variety over a finite field. So the deformation is not just there for the fun of it. Now, and this is much newer, you can still define the random to randoms in the Hecke algebra by using the formula that we had in the symmetric group algebra, not the definition in terms of non-inversions. That one doesn't work. But the definition in terms of b star b divided by k factorial, well, it's a q factorial now. The first sign that this are nice is that this division goes through. You don't end up, no denominators remain, everything cancels. And here is an example. This is R for 2. Remember how R for 2 used to contain every permutation except for 4, 3 to 1? Well, now it even contains 4, 3 to 1. It's just that the factor becomes 0 when Q is 1, which is how you recover the usual symmetric group algebra. And here are the main results. The main results are saying that everything is still true, more or less. Those elements in the Hecke algebra still commute. Those eigenvalues are still, well, not integers, not Q integers, but the next best thing. They are polynomials in Q with non-negative integer coefficients. And if Q is generic, whatever this means, then they can all be diagonalized. We know the eigenvalues too, we know the multiplicities too. There is the same recursion we did before. It's true, except that the integer becomes a Q integer. Well, there is also a weight now. And the same eigenvalues formula is true again with Q weights and Q integers. So I have a sketch of the easier proof of the eigenvalue niceness here. I don't want to comment on it. I don't think I have the time, but keep in mind that it's there and it's kind of tempting. It feels like a pretty lightweight way of proving that eigenvalues of something are integers, but I don't know how generalizable it is. In my experience, there are lots of cases, for example, in graph theory, where a matrix just inexplicably has integer eigenvalues of its Laplacian, and somehow everybody has their own toolbox for it, and sometimes they work, sometimes they don't. I also want to say that for some very simple cases, we have explicit formula for the eigenvalues, but generally it doesn't seem that they're this nice. There are a few open questions, and in particular, you can ask, for example, about the subalgebra generated by the Rs. But at this point, I would like to stop and thank the organizers and thank all of you, and thank quite a few people who have over the years contributed to our understanding of this project.
Okay, let's thank the speaker. Are there any questions for Darij?
You Waterloo is asking something.
I think Waterloo was just clapping for you, Darij.
Oh, okay.
But thanks for the nice talk. But do you mind dropping the link to your slides in the chat?
Right. Yes, because I think this is not the link on the website. The website link is to the older version, to this, which is longer.
Oh, okay, cool.
Yeah.
Thanks.
Thanks. I should have let you know about this.
I know, it was perfect. Thanks.
So I can ask, you said that it was very surprising that these eigenvalues were integers and there weren't that many of them. They had high multiplicities. Would you have any intuition behind that or any reason we'd expect that?
Okay, I mean, if you don't have a reason, because the reason would probably give a short proof, and no, there is no short proof. But, well, they kind of interact nicely with the Young-Uses-Murphy elements, which means that they branch nicely as you go from Sn to Sn minus 1, in the sense that you can, when you like decompose it as n representation in terms of Sn minus 1, you can kind of tell how they interact blockwise with this decomposition. But like just being nice is not enough. This is still a surprising result, I would say. Do I have interpretations for the coefficients? No. Sadly, no.
So you mentioned the techniques for proving that you have integral eigenvalues coming from algebraic graph theory. Is the method that you're using, because you said you couldn't really go through the proof so fast. Like, is the
Yeah,
method
no,
you're using related to those in any way, or is it?
no, I have never. I mean, I don't know them this well, but I have not seen this method before.
Okay.
This is this method. You define a split element to be an element whose eigenvalues are in the base ring, whatever it is, in our case, the integers.
Mm.
And you show that split elements have this kind of nice, I would say, they multiply in the classical sense of this word. So if you have some splitnesses, you can derive some other splitnesses from them.
Cool. And that's just like there's just like no parallel coming from the algebraic graph theories technique.
I mean, okay, I don't know. My impression is that algebraic graph theory people often diagonalize or find eigenvalue vectors.
Yeah. Yeah. That's cool.
This may be elementary, but I know the group algebra of the symmetric group is fundamental to the representation theory. Does the Hecke algebra have some relationship to representation theory of some group?
Okay, so of course it has it's related to its own representations, which are in a way deformed representations of Sn, but more subtly it's also related to representations of GL and of Q. Not to all of them, there are too many, but to certain blocks in a way, not literal blocks, but I mean it comes from it comes from generalizing from I think in a way it comes from LPU decomposition in the general linear group, but that also relates to its representations.
Thanks.
Alexander, I see you raised your hand. Feel free to speak up and ask.
Yes, hi Darij. Quick question. So you quickly, I think there was a slide where you quickly showed the dimension of the subalgebra generated by the R's.
Yes.
I will not. Okay. Do you have any insights, comments, anything about the numbers showing up? About or just this is what it is, data. That's it. You haven't looked into it too much.
I mean, okay, the fact that we were able to compute it up to 12 means that we have some kind of algorithm for it. It's not literally computing, it's not doing linear algebra in QS12, of course. But it is we know the eigenvalues and we know their multiplicities because everything is diagonalizable. Generically, you can just plug this multiplicity. You can just look at like eigenvalue packages. The number of distinct eigenvalue packages is going to be the dimension of the subalgebra. It's bounded from above by some kind of self-convolution of partition numbers, so it's not huge, but it's probably exponential. Well, sorry, no. It's probably something around P of n, I would guess. May is asking about mixing time. I'm afraid I'm not the right person to ask. I think Evitan Estoridi has something about it recently, not at least the q=1 case.
Can I ask a quick question? Thanks for the nice talk, Dari. This is probably a little vague or speculative. A while ago, there was some work of people like Kenneth Brown and Percy Diaconis, which reinterpreted certain results in card shuffling in terms of walks on hyperplane arrangements, like the faces of the braid arrangement. Have you thought about if any of the kind of shuffling things that you're looking at here can be extended to like the braid arrangement or other hyperplane arrangements?
I mean, this is the viewpoint of the original Reiner, Saliola, Welker memoir. They tried to do this with basically instead of BNK, they would take other decent algebra shuffles, and they found only two families that commute. One of them is BNK. The other is the so-called Gelfand family, which we are currently studying, but it feels completely different. It does not generalize to the Hecke algebra. It has a multiplicity freeness property that basically makes it much easier. It is related to various wild things like Pfaffians. We like this family, but it's basically there's only those two.
Okay, and now
Thank
the
you.
next activity from 2 to 2:30 is the discrete objects photo contest. So everyone feel free to walk around and